Okay. Let us get going. Good evening, everyone. And it's a privilege to host Mr. Venkateswara Tanneeru second time. In this month, he almost is giving back-to-back colloquia. It's quite nice on that part. He has actually given on April 13th a colloquium titled An Overview of Global Navigation Satellite System, which is GNSS. And today he's going to talk on where are the satellite-based navigation system accuracies getting inhibited. Of course, we know that TIFR works in balloon facility of TIFR, facility of TIFR at Hyderabad. And for those of you who missed the last colloquium, I would like to take a couple of minutes to introduce the speaker again. Mr. Tanneeru Venkateswara, who is actually known to most of us as simply TV Rao, is working in balloon facility of Tata Institute of Fundamental Research, TIFR, since the year 2000. So he held various positions. Right now, he's of course a scientific officer there. And he mostly works on designing and developing onboard and ground-based telemetry subsystems and satellite-based navigation subsystems. He has received his MTech degree in digital systems engineering from Department of Electronics and Communication Engineering, Usmania University, Hyderabad. That was in 2015, and happy to also share that he is currently pursuing a doctoral degree from Tanneeru Lakshmiya Education Foundation in Andhra Pradesh. That is going to be in the field of ionospheric studies. And therefore, his research interests include GPS, Global Positioning System, amplitude, scintillations, correlation analysis, scintillations prediction, and mitigation algorithms to improve positional accuracy during scintillations periods. So with those few words, I now invite today's speaker, Mr. TV Rao, for his colloquium. And I'm also happy to see quite a few of our colleagues, former colleagues are also on the Zoom. Especially I take note of Professor J.S. Yadav, Acharya, and many others, of course. Professor Ojha is there. So with all that, it's over to TV Rao.
Okay, sir. Thank you so much for the nice introduction, sir. So good evening, everyone. My name is TV Rao, working at TIFR University, Hyderabad. So in this session, I'm going to discuss about satellite-based navigation system. Positional accuracy constants means where the accuracies are getting mitigated or where the accuracies are getting suppressed. So this is the overview of my presentation. I will start with the overview of GNSS, which I have discussed in the previous session. Just discuss about the GNSS overview and GPS GLONASS modernization or modernized signal structures. Signals for ranging estimation or range estimation, errors which are affecting the range estimation, error budget and error correction techniques, and I will conclude with the conclusions. So coming to the GNSS, GNSS is a constellation of, it's a combination of multi-constellation, which are brought into the under one section that is called GNSS, that is Global Navigation Satellite System, which is intended to provide precise timing as well as the accurate navigation data to the user segment. So the first four are the constellations for providing the global coverage of navigation services to the users. And the last two are the regional coverage navigation satellite constellations, regional, for providing the regional navigation services to the users. So the previous section I have already discussed in my previous session. So we'll start with the GPS modernized signal structures, where one can focus because of the advantages in this. So I have indicated in my previous session that there are two concepts called CDMA, Code Division Multiple Access System, and FDMA, Frequency Division Multiple Access System, for identifying each and every satellite. So there are two techniques, CDMA and FDMA. So we will see both the things, CDMA and FDMA, in the case of modernized signal structures. So in the legacy constellation of GPS, in the case of block 2A and block 2R, they used L1 and L2 carrier frequencies for modulating the coarse acquisition code and precision acquisition code onto the L1 and L2 carrier frequency in the case of legacy satellites, means previous satellite constellation. In the case of modernized constellation, modernized signal structure constellation, which is presently available in the constellation. So they have introduced different signal structures, that is L2C, L2M, and they have also introduced L5 frequency for providing radio navigation services to the civil aviation applications, which I'm going to discuss in my next slides. So they have introduced L5 as well as L1C in the modernized signal structures. So this is the modernized signal structure. In the legacy constellation, they have modulated C by A code and P of Y code on L1 carrier frequency, whereas in the modernized signal structures, they have incorporated L1C and L1C of data, L1C of pilot. L1C of data is modulated on BOC, binary offset carrier technique, using that technique, with the navigation data, which is varying at 50 bits per second or 100 bits per second. Whereas the L1C pilot code is modulated on time multiplexing BOC with no data of navigation. So it acts as a pilot signal before giving the navigation data to the user segment. So coming to the L2, in the legacy or in the earlier GPS constellation, they have modulated a P precision code onto the L2 carrier frequency. Whereas in the case of modernized signal structures, they have incorporated L2CM, L2CL, which is the length of 20 millisecond and 1500 millisecond, which is modulated on BPSK. Similar to the L1C, it has modulated with 25 to 50 bits per second of navigation data, that is L2CM. Whereas L2CL is modulated, means not embedded with any navigation data. They also have implemented in Block 3 constellation, constellation with L5 carrier frequency, where the PRN code of length 10,230 bits are modulated on L5 carrier frequency in phase and quadrature phase using the BPSK technique. Similarly, L1 and L2, so L5I in phase modulated signal has incorporated the navigation data of 50 bits per second or 100 bits per second. Whereas L5 carrier frequency with quadrature phase modulated signal doesn't have any navigation parameters. So this is how the modern signal structure has been incorporated to achieve the gain in the case of acquisition or in the case of tracking loop. So this is the modernization. So modernization improves the anti-jamming as well as the secure acquisition. L1C consists of the pilot as well as the data, two components, L1CP and L1CD. So unlike C by A code, L2C, as I indicated, L2CM and L2CL, so which is the civil moderate code. So two distinct PRN codes are modulated on the L2 carrier frequency, which is called civil moderate code and civil long length code. So with this modernized signal structure, we get the accuracy, we get the level, means margin of 2.7 dB in the case of recovering the satellites from the received signal, and we get 0.7 dB greater carrier tracking achievement in the tracking loop. So similarly, L5 provides the signal structure for enhanced performance. L5 signal is broadcasted with I2U protection for aeronautical radio navigation services. This radio navigation services is the technique for providing the navigation information to the users. So this concept I have discussed in the previous session, that radio navigation system has the raised towers where the radio signals are being transmitted for providing the navigation services. The same concept they are now implementing using the satellites for global coverage using the L5 carrier frequency. So L5 carrier signal provides robust as well as secure radio navigation for critical applications like such as civil aviation applications. So similarly, in L5, there are two PRN codes, which is the length of 10,230 bits, which is chipped at 10.23 megahertz, modulated on L5 carrier frequency in phase as well as the quadrature phase. That is how the modernization signals are constructed. Coming to the GLONASS, so far we have discussed about CDMA technique, whereas GLONASS uses earlier constellation uses FDMA technique, whereas in the modernized signal structure, they have implemented the CDMA technique along with the earlier FDMA technique. So this is the legacy constellation where they have used L1 and L2 carrier frequency, whereas in the case of modernized signal structure, they have incorporated L1, L2, L5, L3 carrier frequency along with the L1, L2, and they also have provided CDMA technique. This O indicates the open for civilian applications. The S indicates for the secure applications like military. The character F indicates the FDMA technique, and this character C indicates the CDMA technique. So in the modernized signal construction or the structure, they have incorporated L3 carrier along with the CDMA technique. So coming to the satellite-based navigation system, it is already discussed that it has three components, that is space segment, control segment, and user segment. In this session, I'm going to more concentrate on user segment, that is receiver part. This is the architecture of the receiver, where it has four blocks, that is front end, acquisition block, tracking block, and position computation block. And there is an antenna. So we have two types of antennas, active antenna and passive antenna. Active antenna is to get more sensitivity when compared with the passive antenna. So low noise amplifier will amplify the signal level, which is buried under the noise to the required level, whereas down converter converts the signal into the RF signal into the IF signal, whereas A2D converts the analog signals to the digital signal, received analog signals into the digital signals. Once the digitized signals are converted, means analog signals are converted into digitized digital form, those digitized signals are given to the acquisition block. So acquisition block consists of the n number of channels or n number of microprocessors or DSPs, digital signal processing, where the microprocessor or DSP is generating internal PRN codes, which will be matched with the incoming digitized data. Once it is matched with the particular PRN number, that information will be passed to the tracking block for keeping a track of that, and as well as estimating the range, as well as extracting the navigation parameters from the received signal. Once the range is estimated and once the navigation parameters are extracted, these two parameters are given to the position computation for computing the user position. This is the complete block diagram of user segment, that is receiver. So signals which are coming from the space segment. So as I told, each and every satellite is identified with the PRN code. So there is a 10-bit code, which are called gold codes. So each satellite will be identified that particular PRN code. So 10 bits will be loaded into the shift register. So using G1 polynomial and G2 polynomial, PRN code will be generated. In case of C by A code, the chip length, the PRN code length will be 1023 bits. In the case of PF code, precision code, the length of the PRN code is 10,230 bits. So these two signals are chipped. The C by A code is chipped at 1.023 megahertz. P code is chipped or transmitted with 10.23 megahertz. So coming to the navigation message, the ephemeris, almanac, system health parameters, clock parameters, all put together are distributed in 25 pages of the message. So each page consists of the 5 subframes, and each subframe consisting of the 10 words of 10 bit each. Consisting of 10 words of 10 bits each. 10 words, 30 bits means, sorry, I could not make out that 10 words of 10 bit each. So all these parameters are distributed in 25 frames. So this navigation message is embedded onto the PRN code, and this embedded signal is modulated on the carrier frequency using BPSK, bipolar phase shift keying, BPSK, quadrature phase shift keying, and VOC modulation technique. And this modulated carrier frequency is transmitted to the user segment. So for estimating the range, we have two components, that is carrier as well as the PR encode. If you want to measure the or estimate the range using the carrier, that is called carrier phase measurements. If you want to estimate the range using the PR encode, that is called port phase measurements. So these are the frequencies using in the constellation L1, L2, and L5. And these are the wavelengths: 19 centimeter in case of L1, 24.4 centimeters in case of L2, 25.5 centimeters in the case of L5. So here we have two codes in the PRN, that is course acquisition code and P code. Course acquisition code is chipped at 1.023 megahertz, which is modulated on L1 carrier. This is in the case of GPS. P code, which is chipped at 10.23 megahertz, which is modulated on L1 as well as L2 carrier frequency. And to estimate the range, this is the simple formula: pseudo range is estimated, that is the transmit time to the speed of light. Transmit time is the time of transmission minus reception time. In the case of both the case, means carrier phase measurements as well as the port phase measurements, this formula is same for estimating the range. So determining the position, once the range is estimated and the navigation parameters are extracted from the received signal, so user position can be computed using the trilateration procedure. So if you want to have good dilution of precision, so one should have the widespread of the spreading of the satellites in a widespread. So the poor dilution of precisions when the satellites are very close to each other. So here there are two positionings: one is static positioning and kinematic positioning. Static positioning is the positioning computation when the receiver is at stationary. Kinematic positioning when this receiver is in moving position. So the errors which are affecting the range estimation are categorized into three categories: onboard errors, ground-based errors, and the atmospheric errors. Onboard errors are the selective availability, ephemeris errors, clock errors, and the atmospheric errors are the ionospheric errors and tropospheric errors, and ground-based errors are multipath reflections, receiver clock errors, and computational errors. Now we'll see one by one. Onboard errors, selective availability is the technique of denying the services to the unauthorized users, that is dithering the fundamental frequency intentionally and truncating the navigation parameters from the navigation data. So this is how the selective availability works. So if you want to deny the services, so one can switch on the selective availability. So these are the parameters. So when SA is on, so the positional accuracy varies from 162 to 200 plus or minus in the case of horizontal direction, in the case of vertical direction. When selective availability is off, so we have the 2 to 4 meters of range error. So ephemeris errors, satellite positions are the function of time, and the forces which are acting on the satellite are not perfect, means not constant. So errors in the estimated satellite position known as the ephemeris errors. And satellite clock errors. So even though we provide atomic clocks of cesium and rubidium, which are having the accuracy of 8.64 to 17.28 nanoseconds per day, which represents or which corresponds to the range error of 2.59 and 5.18 meter. So coming to the atmospheric errors, the satellites are placed at about 20,000 kilometer altitude, where the signals are being transmitted from the onboard segment to the user segment. So the signals are passing through the ionosphere, which is ranging from 80 kilometers to 1,000 kilometers, and are passing through the troposphere, which is ranging from 0 kilometers to the 50 kilometers. So the actual troposphere contributes 75% of the tropospheric errors, and the tropopause as well as the stratosphere contributes the 25% of the tropospheric error. Whereas the ionosphere is a dispersive media and the troposphere is not a dispersive media. It induces delay in the propagation radio waves, and sudden or the abrupt changes in the ionosphere causes the amplitude as well as the phase scintillations which are passing through the ionosphere. So coming to the ground-based errors, there are three: multipath reflections. So the signals which are bounced back or reflected from the tall raised buildings or the trees or the plane surface errors, which are getting reflected back to the receiver, and the direct signals. So this may lead to the error because the reflected signal will take the longer path when compared with the direct signal. And there is another problem that reflected signal may dilute because of the collision, it may degrade the signal strength. Those are the two issues one can expect using with the because of the multipath reflections. And receiver clocks, generally the receivers uses the crystal clocks where their accuracy is means they are working at megahertz of frequency. So 1 megahertz means 300 meter error. So the receiver uses less expensive crystals that induces the error about 300 meters if the receiver clock is working at 1 megahertz. Coming to the computation errors, because of the computation power of the processor, which is in the receiver, so that could also introduce the error called computation errors. And the latency of the supporting peripherals also induces the error in the user position computation. So this is the error budget. So the selective availability during the in the horizontal direction, one can expect 100 meters of error. In vertical direction, about 160 meters. Ephemeris errors or less than 1 meter. Satellite clock errors 1.5 meter to 3.6 meters. And ionospheric errors are the largest errors which are getting induced into the computation user positional error, that is 5 meters to 7 meters and more. And there is a possibility of losing the user position also because of the amplitude and phase scintillations. And tropospheric errors, which are very less when compared with the other errors, which is 0.5 to 0.7 meter. Multipath reflection errors, 0.6 to 1.2 meters. The receiver clock can induce the error of 1 meter to 5 meter, and it can go up to 300 meters if they use crystal clocks. And computational errors more than 100 meters, and it can go up to kilometers of error if you use less and processors. So onboard errors, correction, how to correct or how to overcome the onboard errors. So if you want to overcome the selective availability, means that intentional dithering, so implement the GNSS, that is multi-constellation. If one constellation starts selective availability, switch on the selective availability, you take the user position from the different constellation. In that way, one can eliminate the selective availability. That is the main reason for having the GNSS, means multiple constellations under GNSS. So ephemeris errors and satellite clock errors. So estimating the errors and transmitting the error corrected messages. So the the ground station will continuously receiving the signals from the satellites and extract the navigation parameters. In case of any errors found related to the ephemeris or satellite clock, that error message will be computed by the ground segment, the control segment, and that error message will be retransmitted to the onboard segment for corrections. So that is how one can eliminate or one can overcome the onboard errors. And ground-based errors, the multipath reflection errors can be overcome by considering these signals which are received from the satellite above 30 degrees of elevation angle, and by providing the ring structures to the GPS antenna, means circle to the GPS antenna, will eliminate or will overcome the multipath reflections. And receiver clock errors, so using the differencing concept, one can eliminate the receiver clock. So there are concepts called single differencing, dual differencing, and triple differencing. So this is the two receivers with single satellite of single differencing, one receiver with two satellites of single differencing. This is how the receiver clock, by differencing with the other receiver, one can eliminate, means one can by subtracting or by computation. So one can eliminate this receiver clock. And computational errors, by selecting or considering the high-end processors and supporting peripherals, one can eliminate the computation errors. So this is the error. So onboard errors and ground-based errors are fixed variable errors, means they are all known variable errors. Whereas the atmospheric errors, ionospheric errors, and tropospheric errors are dynamic because of the dynamic nature of the ionosphere and the dynamic nature of the atmosphere or troposphere. So these two are the dynamic variables. So tropo and ionospheric errors results positional errors, yes. And at the same time, ionospheric error leads to the losing of the user position because of the amplitude and because of the phase scintillations. That is the main problem one has to attack to mitigate the ionospheric errors. And this is the example of 100 seconds of scintillation period. So during the scintillation, there is a sudden fall of the carrier to noise ratio beyond the certain level, where there is a possibility of losing the acquisition track and losing the tracking loop of that particular satellite, where one could not compute the user position. Then there is a possibility of losing the user position during severe amplitude and phase scintillations. So coming to the tropo and ionospheric, these two errors, whether they are good or bad. Good for the research community for doing research on ionosphere and troposphere, bad for the other applications. To overcome that, remove the atmospheric errors for the satellite-based navigation applications to have a better, good user position computation, and use them, the tropo and ionospheric errors, for understanding or for studying the ionospheric characteristics and tropospheric variabilities. So that is good for iono and tropospheric researchers. So coming to the troposphere, as I have indicated, the height 0 kilometers to 10 kilometers is the actual troposphere, and the tropopause is considered from 10 kilometers to 16 kilometers, and stratosphere starts from 16 kilometers to 50 kilometers, and above 50 kilometers to 80 kilometers is considered as mesosphere. Even though the tropospheric errors are less, that is 0.5 to 0.7 meters, and also the troposphere is electrically neutral atmosphere, and this is non disruptive mechanism. So coming to the error mitigation or error overcoming. So even though it is very less, 0.5 to 0.7 meters, by estimating the ZTD, that is zenithal total delay, one can overcome the tropospheric errors. So coming to the ionosphere, so ionosphere exists between 80 kilometers, 1,000 kilometers, with different layer names D, E, F1 and F2 during the daytime. Whereas in the nighttime, D, E layers will disappear and F1, F2 layer will become F layer. And the ionosphere is very dynamic, and it's called the complex construction. So the ideal characteristics of the ionosphere is getting disturbed because of the space weather events from the top side of the ionosphere. And the ideal characteristics of the ionosphere is getting disturbed because of the neutral winds from the bottom side of the ionosphere. Apart from space weather events and the neutral winds, anomalies are also affecting or disturbing the ideal characteristics of the ionosphere, which are equatorial ionospheric anomaly, that is EIA. That is because of the E cross B fountain effect at the equatorial region, and post-sunset equatorial plasma bubbles, EPBs. That is because of the sudden falling of the ionization levels from the sun at the post-sunset hours, during the sunset hours. And these irregularities, ranging from few kilometers to thousands of kilometers, traveling from one place to the other place, are creating or disturbing the ideal characteristics of the ionosphere. These are all the anomalies. So space weather events, neutral winds, and anomalies are disturbing the ideal characteristics of the ionosphere, which are creating irregularities in the ionosphere indirectly, which are disturbing in the amplitude or in the phase. Those are all called the scintillation, which are the radio signals which are passing through the disturbed ionosphere. And these scintillation depends on many factors like solar zenith angle, thickness of the layer, signal frequency, local time, seasonal changes, and solar and geomagnetic activities, and so on. The ideal characteristics and irregularities of the ionosphere can be measured or can be monitored and can be recorded by various ground-based sounders, ground-based digital ionosondes, top-side sounders, sudden ionospheric disturbance monitors, and GNSS receivers. This is the one of the example of the ground-based ionosonde, that is digital ionosonde, CADI, Canadian Advanced Digital Ionosonde. It is having the specification of 600 watt power, frequency range 1 to 20 megahertz, 1 to 400 linear or logarithmic steps per sweep, and it can cover the 92,024 kilometers height with the height resolution of 6 kilometers. And it has the two provisions: sounding vertically 90 degrees, and it has a oblique sounding facility also, it is there. This is the example of the digital ionosonde called ionogram, which reveals the characteristics of the ionosphere. So these features or the parameters of the ionogram reveals the characteristics of the ionosphere. So here E stands for E layer, ES stands for sporadic E layer, F stands for F layer, F1 and F2 stands for F1 layer and F2 layer. So H dash means virtual height, that is the starting point of the trace, whereas the FO is the critical frequency, that is the peak frequency which has reflected from the ionogram, ionosphere. And SF is the spread in case of any irregularities that will be reflected in the ionograms in the form of spread F. And in the case of E layer disturbances, irregularities, that will be reflected in the ionograms in the form of sporadic E layer events. So with this parameters or the ionospheric features, one can understand the characteristics of the ionosphere. So CADI can be used to understand the characteristics of the ionosphere. The other component is the GNSS receiver or the satellite-based navigation receiver, which gives time, azimuth, elevation, amplitude, as well as the TEC parameters directly after computation. So this is the example of the data sample. So it gives the week number, time of week, pair and code, azimuth, elevation, carry to noise ratio information, S4 parameters, amplitude scintillation parameters, and TEC parameters, and so on. So coming to the TEC, which is the most important point or most important component of the ionosphere, where TEC is the integration of all the electrons between 2 points along the tube of 1 meter square cross section, and TEC measured in TEC units, TEC units. So we have two TECs, that is vertical when it is measured on the local zenith path, and the slant TEC when it is measured beyond or above the means different from the vertical local zenith path. These are the formulas for measuring or calculating the VTC as well as STC. So TEC is a very complicated quantity which varies, which it depends on the diurnal variation, seasonal variation, solar cyclic variation, and it get affect with the sunspot activities, line of sight position of the observations, and so on. So determination of the TEC is very, very important. It is very crucial. TEC effects needs to be measured, estimated, model, or eliminated. So this is how the TEC is estimated using the digital ionograms data. So once we extract or once we scale the FO2 parameter, that is critical frequency of the F2 layer, so one can compute the TEC using the navigation data. Navigation data, it directly gives the TEC by computing, by considering the F1 and F2 carrier frequency of pseudo range, that is P1 and P2 pseudo ranges. So 1 TEC unit is equivalent to 1 into 10 to the power of 16 electrons per meter square. 1 TEC unit corresponds to 0.163 meters of range error in the case of L1 carrier frequency, and that is 0.268 meters of range error in the case of L2 carrier frequency. So how to eliminate the TEC? The best way of eliminating is considering the 2 carrier frequencies. So the most efficient method is to eliminate the TEC, because in most of the cases, it is very difficult to measure, estimate or model the value of TEC. So the best way is to eliminate the TEC. How to eliminate? By considering the 2 carrier frequencies. So by implementing the linear combination of the pseudo range model, will cancel out the ionospheric refractions. So that is the best way to eliminate the TEC errors. So that is the reason most of the constellation uses 2 carrier frequencies. So L1, L2 in the case of GPS, L5 and S band in the case of IRNSS. So user position loss. So far we have seen the errors which are affecting the user position, and we have seen how to overcome the effects of the errors. So multi-constellation, that is GNSS to overcome the selective ability error, continuous tracking, monitoring, and estimating the onboard errors, and uploading the error correction message to the onboard segment is to overcome the onboard errors. And single differencing, dual differencing, and triple differencing concepts are implemented to overcome the receiver clock errors. And considering the 30 degrees, above 30 degrees elevation angle received signals, and implementing the round ring structure, metal structures around the GPS receiver is to overcome the multipath reflection errors, and estimating ZTD to overcome the tropospheric errors, and implementing dual carrier frequency to overcome or to suppress the ionospheric errors. Even though errors are minimized or errors are tackled, so there is a possibility of losing the user position because of the ionospheric scintillations, which are affecting the amplitude as well as the phase of the signal which is passing through the irregular ionosphere. So that opens the window for the research work, that is the scope of research work. So far, a large means a wide variety of research work has been done in estimating and predicting the TEC and amplitude scintillations and ionospheric features such as FOF2, HMF2, and spread of parameters using various techniques. So that is using the neural network methods, by using the deep learning techniques, by using the CNN convolutional neural network. One has means they have developed they did the research work in estimating and predicting. And also implemented means the research work has been done in implementing the scintillation mitigation algorithms for improving the satellite acquisition, the block, and also improve the tracking loop block for improving the accuracy by reducing the errors. So these are the algorithms we have implementing the fast Fourier transformation in the acquisition block for improving or for mitigating the scintillations, and implementing the Kalmar filter based PLLs in the tracking loop will mitigate the scintillation, and wavelet type denoising procedure and wavelet detrended techniques are already implemented for offline as well as the real-time applications. So that much research work has been done. Still, there is a scope of estimating the spatial variations of the TEC using TEC maps with various techniques like image processing technique or convolutional neural network, and developing the amplitude and phase scintillation mitigation algorithms to improve the satellite acquisition methodology, that is algorithms, during severe amplitude and phase scintillation for real-time applications, for application point of view. And still research work, there is a scope of research work for improving the receiver satellite tracking section, tracking loop algorithms to sustain the tracking loop during severe amplitude scintillations in real-time applications, means application point of view. So coming to the conclusion, yes, satellite-based navigation systems are developed for providing meter level and centimeter level accuracy. And there are differential GPS concepts are there or implemented to improve the positional accuracy. And multi-constellation concepts were brought like GNSS for improving the positional accuracy and system augmentation. So sorry for not addressing the augmentation concept because of the time constraint. And the systems augmentation concepts were implemented to improve the positional accuracy, which is useful for the civil aviation applications. Still, wide research work is going on in the application point of view to improve the positional accuracy with the different techniques. My question is why and where the accuracies are getting suppressed or inhibited, even though satellite-based communication system is developed for providing meter and centimeter level accuracy. Thank you.
Yeah, thanks, TV Rao. Firstly, I'm sorry, somehow there has been a challenge from my end. TIFR, for quite some time, there has been an unstable internet. Probably, I hope the problem is resolved. So because of that, several times I was kind of logged out, so I couldn't be hear most of the talk. But I know some of my colleagues here also probably were affected by that internet outage. However, for other audience, the talk has gone without interruption because I made you and Professor Vivek Datar as the co-hosts. So the meeting continued, the talk continued, and also there was no issue on the YouTube as well. Okay.
Okay.
But I'm sorry, this was completely out of my hand.
Okay.
Also,
that is from our side, sir.
No, not from your side. It is TIFR Mumbai.
Okay.
Yeah. So it's a institute-wide some issue. Maybe we'll see the reason a little later, but at the moment it looks stable and back to normal.
Okay, sir.
So just one point before I take some questions. You still have some time in case you want to cover this system augmentation.
No, sir, I have not prepared any slides for this segment.
Okay.
So I can say that augmentation has been incorporated or implemented for the civil aviation applications where the safety of the life comes into the picture. So to provide uninterrupted services. So here we need to consider 4 points, that is availability, continuity, integrity, and accuracy. So these 4 points are very, very important in the case of civil aviation applications where the safety of the life comes into the picture. So in that case, the augmentation system has been brought like WAS or LAS, wide area augmentation system. The satellite-based navigation system is satellite-based augmentation system, local area augmentation system for local usage. So in that we have SBAS, satellite-based augmentation system, and aircraft-based augmentation system, ground-based augmentation system, and so on. So that is also a big sub topic. So if I find time sometime, then I will take up that also. Yeah. Right now I have not prepared any PPTs on that, sir. I mean, the slides in the PPT. Yes, sir. Anand, sir, please go ahead, sir.
Yeah. Thank you, Tira. Yeah, it was nice listening to your talk. I have a few questions.
Yes, sir.
I'll ask one by one. Okay.
Sure, sir. Yeah.
So now selective availability.
Yes, sir.
Okay. Though the Pentagon has said that SCI will not be implemented. Okay. So they have said basically because it's US Department of Defense maintained GPS constantly.
Yes. US based.
They can implement in cases where there is war and so on.
Yes, I think if I'm not wrong, we have faced the SCA during one of in the balloon flight during the Kargil war.
Iraq, Kuwait. Huh?
Yes.
Yeah, it's possible they can. But
Yes.
now what I want to ask is, how much does SCA create an inaccuracy in position?
So in the case of horizontal position accuracy, it is about 100 meters. In the case of vertical position accuracy, it can go up to 160 meters.
Okay, but earlier they were saying 300 meters. Okay, fine.
Okay.
So now, it's okay.
When you see the graph, that is 100 to
it may have improved over
300 meters is in the case of receiver clock, sir.
Yeah.
So 1 megahertz means that is 300 meters.
Yeah. So now, to suppose SA is implemented.
Yeah. Means switched on.
Switched on, right.
Okay. Yeah.
So which means we have to live with the errors, or is there any way to mitigate those SA errors?
Yes, sir. Here, that is the reason the GNSS concept has come. So if you are agree or if you are okay with those errors of 100 meters or 200 meters or 160 meters, then you can use that constellation. If you want precise positioning, then go for the another constellation.
Yeah, which means that you have to have multi-constellation capability receiver.
Yes, GNSS receiver. Yes.
So you need to have like GLONASS, Vidal, and Galileo, and the GPS, all
GPS.
4.
Yes,
okay.
Yes.
So that's the only option. Otherwise, there are no mitigation techniques.
No, sir.
No mitigation techniques, yes.
Yeah, I don't think so, sir. Yeah.
Yeah, fine. And the second question I want to ask is this dual frequency usage to to overcome the errors in the ionosphere caused by the ionosphere. Okay.
Yes.
So that's a good concept. We have, but I see that Indian Regional Navigation System
Yeah.
uses L band and S band.
Yes.
Okay, while the GPS and others use L band only.
Yes.
Though
In
the-
L band, they
Yes.
use two carriers, L1 and L2.
L1, L2. We are using L5 and S band.
S band.
There's a big difference in the frequency. Okay.
Yes, yes.
So in that case, which do you feel? Which do you feel? Indian Regional Navigation System will give you better ionospheric corrections, or the GPS and Galileo and so on?
Still, the regional IRNSS has not stabilized yet in providing the accurate navigation parameters, and still work is going on to implement or take up the L1 band frequency in the further upcoming satellite constellation. So better is the GNSS, because still we are in the testing phase only. Means
Yeah, of course,
implementation
this is
phase has
reasonable.
come. Yeah, implementation phase has come, but still errors are more in the case of IRNSS, and still research work is going on to reduce the errors.
Yeah.
So in that point of view, GPS is the best way.
Better,
Yeah.
Okay. And my final question is,
Can I ask a question?
Yeah,
Sir.
Sir, we'll come back, Professor.
Manchana, sir.
You ask your question again, we'll come back to Professor Anand. Yeah.
you want me to ask or?
Pardon?
Yeah. You please ask.
Okay.
Yeah, okay.
Manchanda ji, yeah.
Manchanda.
I have one first short question. Is CADI still working?
No, sir.
Okay. Second, I didn't pick up in the differential mode. What would be the what is the error of the height? Because for autopilot of a plane, 150 meter inaccuracy is the dangerous. So
Yes,
does
sir.
it become just of the order of a meter or so? Because wrong estimation can lead to the accident.
Yes.
So yeah, what is that in differential mode? What is the height errors?
Height errors is below 1 meter, sir.
Below 1 meter.
Yes.
Okay, but just a comment on the S band.
Yeah.
S band is less prone to the ionospheric disturbances.
Yes.
Yes.
Because- And also, it's a signal you can detect even at low wattages from a far distances.
Mhm.
So
Yes.
S band has a certain advantage in reception. Since it's a regional, you are not seeing it across the globe, while L1, L2 frequencies can see up to long distance.
Yes, sir.
Absolutely right, sir. Correct. Yeah. And I just want to ask one question, TV Rao.
Sir,
Okay.
yeah.
Now you see, finally we are into now using the space-based augmentation system.
Yes.
Like, what Professor Manchanda was talking.
Yes.
Now, basically, instead of saying the differential system, we should say S-bus.
Yes, boss.
There
Yes.
is no
So-
differential now, ground-based. It's all space-based augmentation system.
Yes.
Okay.
Where the error signals are directly communicated to the
Okay,
civil
Fine,
aviation.
fine. It's only
in
the
local.
way is different.
Yeah.
Earlier it was ground-based, terrestrial-based corrections were sent, and
Yes.
now it is
Space-based.
satellite-based corrections are being sent.
Yeah.
Okay,
Yes.
like WAS for the American region, EGNOS
Yes.
for the European region, and
Gagan
for
is
the
for-
Indian region.
Yes. Yes. Gagan.
So now they are all basically meant for providing precision landing
Yes.
approach for the aircraft and so on. Okay.
Yes. Yes.
Now Gagan has been implemented, and I just want to know that if Gagan was used any time in the Indian region for precision landing system, whatever Cat 1, Cat 2, I don't know, any time whether Gagan was used by an aircraft for landing.
That I don't have much idea, sir. But
Okay.
Gagan receivers are there in the
Yeah.
airports. In Bangalore airport, it is there. In
No,
Hyderabad.
we have in our transponder Gagan receiver. Okay.
Okay.
Our modest transponder
Whether it has been.
for S-bus. Okay. We
Okay.
have that basically.
Hmm.
So I'm just trying to understand if it was
It has
really
been-
used for precision landing by aircrafts and so on.
Yeah.
We can
So
try
it-
to find out. Yeah.
Yes,
It is actually meant for the Airport Authority of India, means
Yeah.
civil aviation application that has been brought. So that they may be using, sir, but
Yeah, we have to find
I
out.
don't have idea, sir. Yes,
Can I
have to find-
add? One
sir.
attempt was made successfully to land with Gagan.
You're right.
Paul told me, he was in charge for the whole system. And he told me that it was successfully done. So it
Okay.
will be implemented and autopilot in some time.
You're right. Actually, it was done last year. I was not sure about it. So I asked TV Rao. Right. Correct, sir.
Okay. Yes, thank you for that discussion. Anyway, again, I'm back, but somehow I don't know when it will again disrupt. Any other questions from the audience? Zoom? TV Rao, can we actually go? I have a small question for you. I don't remember the slide. I think you don't have slide numbers. Somewhere in the
slide numbers are there, sir. Okay.
no, because it was getting cut. So
Okay, fine, sir.
I think maybe you have. In the very beginning, 4th or 5th slide, probably where you talk about the receiver system.
Okay, receiver. Yes, this is the one.
Yeah, this one.
Sir.
So you seem to be here talking about a very conventional system where you have analog on one side and microprocessor or DSP on the back
Yes.
end.
This is the typical architecture, sir.
Yes, that's right. But with now the system on chips, especially RF SoCs, etc.
FPGAs. Yes.
Is there a kind of a more simpler or a multi-channel kind of a system that is getting possible or still?
Yes, sir. Yes, sir. Things are getting, things are going on, sir, with the SoCs as well as the ASICs or the FPGA receivers are coming up. Yes, this is the typical thing which I have explained you. So the older version, you can say, which are having microprocessors and DSPs. Still DSPs are being used, even though you use FPGAs, internal DSPs are used for correlation of the incoming signal. Hello.
Yes. Yeah. We are able to hear.
Okay, my again line might have cut.
I think Dr. Tanneeru seems to be out.
Yeah.
Okay, so they have some internet issue, I think, sir. Yeah.
Is there any other question?
No. From my side.
No? Okay, then maybe in the absence of Dr. Satyanarayana, who should be actually doing it, then maybe we can
just
close
came
this.
back.
He's come back.
Again.
But I
do the
missed his on.
Answer.
But I will talk to him. Sir, you can go ahead and please conclude the session. Anyway, I was on.
No. You go ahead. You're there right now. No problem.
Sorry.
So,
really...
sir, Satya, sir, see, nowadays the receivers are getting developed using FPGAs. Yes, the trend has come and people are working on FPGAs itself or SDRs itself. Software defined radios. Yes, yes. They are implementing GNSS receiver on SDRs.
So therefore, naturally, the complexity of what you showed here on this slide or
yes, that has
to kind of shrink very drastically, and of course, probably will make it now. People talk about 16-channel RF and one chip and so on, all through end to end.
End to end, yes, sir.
So it's very interesting development, and I guess your field too is getting benefited by.
Yeah, our actual motto is for the application point of view, sir, to implement the mitigation algorithm in the receiver itself while developing. So that is our main aim. Yeah.
Very.
Can I ask this slightly? It's
yes,
not
sir,
exactly related to this, but maybe indirectly related to that. Is that okay?
Please, sir, go ahead.
Please go ahead, sir.
Let's say in the landing of spacecraft, maybe from the mother module or something on let's say moon or maybe even Mars. What is the kind of requirement on the accuracy in position and so on that is required of these modules that land?
So they will have
the order of maybe tens of centimeters or something, or maybe
they will have the stages, sir. So with the accuracy of GPS, they will go up to certain level, and they will have the INS inertial navigation system.
Okay.
So where it is a combination of IMUs, inertial measurement units, as well as GPS up to some extent, and they will go with the laser technology to get centimeter level of altitude accuracy.
So they will be communicating with the mother module, is it?
Mother module. So levels of accuracies are there. So up to certain extent, they will go with the GPS. Up to some extent, INS units, and for precise and all centimeter level accuracy, they will go with the laser technology and all. Yeah, they will be already incorporated in the
No,
system.
Vivek, no. This cannot be done like this.
Yeah.
You see, when you want to land on another body, celestial body, you are actually mothership is orbiting on a celestial body.
Yeah.
And then what happens is that the lander separates. It has a free fall. It just cannot analyze its position till the parachutes open. The big
No. I'm talking about, let's say, on the moon.
that's what I'm telling. Even on the moon, you have to slow it down.
Correct.
So you slow it down with the jet.
Correct.
So once you slow it down, then they start ranging. The lander itself ranges its distance and optically determines the position it has to go.
Okay.
It's able to move laterally in all directions
Okay.
to actually land the position it has been marked.
Okay.
So mothership, it is only telemetry. And in the case when the lander is on the other side of the moon, so it's a completely different story.
Yeah.
So the problem is that what failed in our case was that jets probably did not work properly, lateral jets, and it went into some sort of tumble.
Yeah. It became
unstable.
Unstable. Yeah.
Unstable. So tumbling means it fell down, basically.
Okay. So if there are any other questions, you can take them. Otherwise, then we can probably thank the speaker for a nice colloquium.
Thank you.
Thank you.
Thank you so much, sir. Thank you so much for the inputs and suggestions.
It so happens that Satya called me just now. He says he's right now out of the loop. So I do this on his behalf. Thank you very much.
Fine, sir. Thank you so much for giving the opportunity, sir. Thank you so much. Yeah.
Thanks,
Okay, TV.
Yes, sir. Manchanda, sir.
Thank you.
Thank you so much for the information, sir.
You still did not tell what you did. You have papers on it. This is what I was expecting to tell, at least what you did. You didn't tell.
Sir, that is entirely different, sir. My analysis is different. And of course, my analysis turns towards the application point of view. I want to turn towards the application point of view.
That is okay. That's okay. But you should have brought in your work in it.
Oh, okay.
Right.
And since you are pursuing currently thesis, maybe Manchanda sir wanted to also hear flavor of what that is. Maybe.
Yeah.
No. I read his paper, but I wanted him to say that.
Okay. So,
fine, sir. Definitely.
So once again, thanks, TV, for both of your talks. And I also want to sincerely thank Professor Datar, who saved the situation. It's really sad that I think there is some severe problem here.
Yeah.
But good that at least at the end there was enough time to kind of thank you, all of you, and thanks everybody, Dr. Anand, Dr. Manchandas, and Professor Datar, and all other colleagues who are on the call today. Thanks a lot, TV, and
thank you so much.
PhD work.
Okay.
And we soon want to hear one more talk after you defend your thesis successfully.
Sure, sir. Definitely, sir. Yeah.
Thank you, everyone. Thanks.
Thank you so much, sir. Thanks for the opportunity. Thank you, sir. Yeah.
Bye-bye.
Bye, sir.